These are the AP review questions for the Chapter 16 and 17 test. So this is the first video, which covers Chapter 16, and then we'll do a second one for Chapter 17. Remember, Chapter 16 is all about acids and bases individually. Chapter 17, we're putting them together. So the first question asks us, the reaction represented above is observed to proceed spontaneously to the right in aqueous solution. So here's the reaction. In this system, the strongest base is. Now what we see is that the HSO4- reacts with CO3 2- to form SO4 2- and HCO3-. What you see is that this substance acts as an acid because it gives away its H+. So this is your acid. Now the carbonate acts like a base because on the right side it shows up with an H+, which means it's accepted. So it is the base. Now, because this is an equilibrium system, we can think from the right side as we go back to the left. The SO4 acts like a conjugate base because it accepts a proton. So this is this conjugate base. And HCO3 acts like a conjugate acid, going back the other way. Remember, because of equilibrium, we can now think of these as going both directions. So the question is, which is the strongest of the bases? Well, it comes down to this substance and this substance because they are the two that act as bases. Now, if we remember, CO3 originally came from carbonic acid, which is H2CO3. That you can think of it coming from carbonic acid, whereas SO4 2- came from sulfuric acid, H2SO4. So remember, we said the stronger the acid, the weaker its conjugate base, and the weaker the acid, the stronger its conjugate base. So because this is a strong acid, sulfuric is one of the 7 strong acids, whereas carbonic is not, which means it's a weak acid, its conjugate will be stronger as a base. So this one is actually the weaker acid, which means its conjugate is the stronger base, which means the answer is carbonate. Okay, number 2 asks about caffeine, which is a weak base, giving us a Kb value of 4 times 10 to the negative 4. The pH of a 0.01 molar solution of caffeine is in the range of one of these. Now, these AP exam questions actually do not allow you to use a calculator. So what we would need to try to do is calculate the pH of this without using a calculator. Now, the way we calculated the pHs of weak acids and weak bases is by using the icebox or the shortcut to the icebox, which, remember, told us that if in this case it's a base, OH-, the concentration of it is the square root of the Kb times the concentration of the base, which you can say concentration of the base, like this. So in this case, we have the square root of our Kb is 4 times 10 to the negative 4th, and our concentration is 0.01, so multiplied by 0.01. Now, when you multiply something by 0.01, you're moving the decimal place left twice. You're multiplying it by 100th, which means this becomes negative 6. So we actually have the square root of 4 times 10 to the negative 6th. Now, square rooting 4 is easy enough. Square root of 4 is 2. And then square root of times 10 to the negative 6, 10 to the negative 6, the square root of this is actually 10 to the negative 3rd, which may sound a bit confusing, but what you have, square rooting something is actually raising something to the 1/2 power. You could think of 10 to the negative 6th raised to the 1/2 power. And then if you recall that if you have powers, you would actually multiply them to get you 10 to the negative 3. So hopefully this makes sense. This is more of a math trick. So if this doesn't make too much sense, then think through it, and possibly you could see the math there. And then what we have to do, we have the concentration, the OH- concentration. We need to find the pH, which means we need to negative log this. Well, negative log of 2 times 10 to the negative 3, you say, well, that's even tougher. But remember that the negative log pulls out the power. Now, if I had, it's getting a bit crowded, but if I had 1 times 10 to the negative 3rd, the negative log of it is 3. If I have 2 times 10 to the negative 3rd, that means that's closer to 10 to the negative second, which means we're probably between 3 and 2 for our value. So the negative log of this number is going to be between 2 and 3, or 3 and 2. Again, pause the video, think through this. This is kind of doing math without a calculator. And so since in this case we got the POH, if we negative log it, the pH then would be from 11 to 12. Now this makes sense. You might have figured this out actually just by looking at it and thinking about it logically. We have a weak base, so its pH cannot be low. These are acidic pHs, so out, out, out. Now this one here may be a possible choice, but this one is actually very close to neutral. And a weak base with a Kb, considerable Kb, will be quite a bit more basic than 7 or 8. So you could have probably guessed this without even doing the calculation. But the calculations were fun, admit it. Okay, so let's try the next set of questions actually references a table. And this is the table it references. So we're given the pH of 4 acids prepared. A bit lower here. pH of 4 acids prepared at various concentrations. It'll do it. Doesn't want to stay. Is given in the table here. So we have 4 acids, 1, 2, 3, 4. The 4 acids, in no particular order, are chlorose, hydrochloric, lactic, and propanoic. And the thing to recognize is that hydrochloric is the only strong acid here. The rest of them are weak acids because they don't fit into one of the categories of strong. Question number 4 says, for which acid is the value of the acid dissociation constant the smallest? Okay, so what we're seeing is each of the 4 acids is given a pH at a certain concentration. So, going from 0.01 and all the way up to 1 molar. So looking at this row right here, we're seeing that pH of acid 1 is the highest. Notice it's 3.44. pH of acid 2 is the lowest. Now, the stronger the acid, the lower the pH would be. Remember, if an acid is strong, that means it releases all of its H+. So if the acid HA in this case is strong, it releases all of its H+, and no more of this remains. But if an acid is weak, it releases only a little bit of its H+. If it releases a little bit of it, that means its pH will be the highest. So for the weakest acid, the one with the smallest Ka, remember if the Ka is small, that means we have a weak acid, its pH is going to be the highest. And that indeed is acid 1. So we had acid 1 with the highest pH, 3.44, which means it is the weakest acid with the smallest Ka. Number 5 actually asks the opposite thing. It asks which of the 4 acids is hydrochloric, which means which is the strong acid. Now, this would be the one with the lowest pH, and indeed, this is acid 2, the lowest pH, having a pH of 2. In fact, if you negative log 0.01, negative log of 0.01 is 2, because 0.01 is actually 10 to the negative second, and negative log pulls out the power, which gives you the 2. So we know that acid 2 is actually hydrochloric acid. So let's see if I can clear this up a bit. Now, 6 says, of the following species, which has the greatest concentration in a 1.0 molar solution of acid 1 at equilibrium? So we've already said that acid 1 is a weak acid, and if a weak acid dissociates, not all of it will dissociate. So at equilibrium for a weak acid like HA, you still have a lot of reactants and a little bit of products. So it dissociates partially, produces a little bit of H+, which means most of it will still be in the acid 1 variety. In other words, the H3O plus would be this amount. The OH minus, it's an acid, not a base, so the OH minus, not much of it will be there. The conjugate base is this substance. So both the H3O plus and the conjugate base are actually in small amounts compared to the acid. How about number 7? If equal volumes of the 4 acids at a concentration of 0.50 are each titrated with a strong base, which will require the greatest volume of base to reach the equivalence point? So what we're saying is we're going to neutralize all 4 of these, completely neutralize them. And which one will require the most base? Well, it turns out it doesn't matter how weak or strong the acid is, it can neutralize the same amount of base. So the answer is actually D. That's because even if it's a weak acid, it still has the same amount of H plus available to be neutralized. It just doesn't release it all at the same time. A strong acid just releases all of the H plus right away. A weak acid releases it little by little, you can say. But in a titration, all of the acids will require the same volume. All right. So that wraps up that question. We have one more question down below. Let's take a look at it. Another table and another equation. This is actually the famous auto-ionization of water equation. So we said that water does this in pure water. If you have a bottle or glass of pure water, it dissociates, breaks apart into its 2 ions. And here, the kW for this system is, we said, 1.0 times 10 to the negative 14. But this was at 25 degrees Celsius. In fact, every dissociation constant, every K, is given at a certain temperature because temperature has an effect on K. Now here, what we're given is we're given different temperatures and the corresponding pKW. Now, the pKW, if you negative log your kW, you'll get a pKW. This is what the negative log means, but the pKW then will be 14. If you negative log at 25 degrees Celsius, you'll get 14. And you'll notice that it fits right in here. Oops, I'm sorry. It fits right in here. So we're actually, we would be right here. So what they're telling us is that the higher the temperature, the lower the pKW. What this means is that the higher the temperature, as temperature goes up, your kW, since your pKW gets smaller, that means your kW, this number right here, gets smaller and smaller. So we get 10 to negative 13, negative 12, negative 11, which means the number itself, the kW itself, goes up. So as temp goes up, kW goes up. And this is a weird way of saying it, but that's, if you think through it, that's exactly what's happening. Now, if the kW is going up, if our constant is going up, then our ratio of products over reactants is going up. Because our products now is going up, our reactants is going down, which means we're forming more and more and more product as temperature goes up. Now, since we're creating more and more and more product, we're creating more H3O+, which means the solution is getting more acidic. If the solution is getting more acidic, that means the pH is going down. So the answer is actually this one. As the temperature increases, the pH of pure water decreases. So now this logically makes sense because here what we're showing is that water is breaking apart into its 2 parts. So the hotter the temperature, the more energy you put into the system, the more it'll break apart into these. That makes sense. Which means the higher the temperature, the more H3O+ we form, the more H3O+ we form, the more acidic water is. So at a higher temperature, water is more acidic than at a lower temperature. Some facts to share with a friend. Okay, so this idea of kW and pKW very often is actually convenient. And sometimes instead of getting the Ka of an acid, they'll give you the pKa of an acid. And so the weaker the acid, the lower its Ka value. So say a really weak acid will have a Ka of 1.5 times 10 to the negative 7, for example. Your pKa will be like, 7.9 or 7.4, something like that. So the weaker the acid, the higher its pKa. So we can say that here. The weaker the acid, the higher the pKa. So an acid with a high pKa will be very weak. An acid with a low pKa will be very strong. All right, hopefully this sort of makes sense. Think through it, go through it, and we will answer questions in class.